Beer here again. Undergraduate marketing major, BIA minor from the University of Denver. Today, or for my last session of the day, I went over to it was a conversation on understanding like the future of quantum tools and how they're going to help us like grow and do things that we were never capable of before. And to begin with, I should say I have no current understanding of deep quantum mechanics or what quantum computing really is at its core. I know at a baseline that it is much higher level computing than what we have available to us on a mass level, and it's capable of like solving problems that would take hundreds or thousands of years for our computers to solve today. But like in a millisecond, it'll have that information to you immediately, and it'll always be the right answer. And it's something that I didn't really, again, being there, all of the jargon they were using was going right over my head. There were a couple terms I learned about that I found really interesting, and they had some really good analogies that I thought helped kind of make sense of what they talked about in the meeting. But it was kind of hard understanding bits and pieces of it just because he was saying words that I had never heard before, let alone were used in such a high level setting. Um, in terms of this, it was the D-Wave chip that they were showing off, which is this new quantum computing chip that D-Wave is creating. But from what I understand, it goes contrary to a lot of other quantum computing chips. In some way, at its core, it's using superheating instead of superposition or something like that, or superheating instead of supercooling or something to induce the superposition of the quantum mechanics. I really don't understand the jargon. I'm trying to get across as best as possible, but how they explain it is they're making programmable quantum matter so that people all around the world can tap into the network and be able to program the quantum computer to do whatever they need it to do. It's not that simple, and the average person couldn't just walk up to the computer, type in, "Hey, I need you to do 1 plus 1 and solve that for me." Like you wouldn't just be able to do that. But if you understand how it works and like are knowing what's going on, then you can use it to solve problems that wouldn't be possible in tens of thousands of human lifetimes, let alone using normal computers today. What they were saying is it's taken 20 years for them to build what they have right now. And it's been like some insanely hard work over and over again. And in the one chip, there's over 5,000 qubits and 4,000 interactions between those qubits. Again, I don't really understand what a qubit itself is or how that relates to quantum mechanics as a whole, but how they explained it is most of the computing we have now doesn't use one one thousandth as many qubits as we're using in quantum computing, or and the capabilities because they use so many are like outside of the realm of our understanding as humans right now. Kind of like how when you talk about $1 billion, you kind of say $1 billion, but like you don't know what that means. That's what quantum computing is to compared to regular computing. Like it's an unfathomable amount of power at our fingertips to solve problems we didn't even think were possible to solve. Um, let me try and find it exactly. They had a really great analogy they were using where they have a process called, let me find it to make sure. Basically, they're kind of using the D-Wave technology is kind of like they are quenching almost, or not quenching, it's like they're quenching metal at a quantum level. They're taking the baseline information, they're using superheating to induce it to kind of like almost like you're heating your metal in the oven. You're making a sword, you're trying to get out any imperfections, and you take it out of the heat, you hammer it down, get out those imperfections, you quench it, you throw it in the cold water, and you then are removing the imperfections and getting it to the exact sword that you want it to be. At a quantum level, they're basically taking what information you're programming into it, superheating the elements inside of it, inducing a state of superposition, which again, I don't really understand what a superposition is. and then that cools down into essentially the idealine crystal shape that you're looking for with your answer in it. So another way they were explaining it was that like if you wanted to make a map of Colorado, you if you like as a person were doing that, you'd start at the tallest mountain, you'd kind of like look at your landscape, do that, and then if you were looking to find the low like a topographical map, you're looking to find the lowest point next. You'd look around and you'd be like, oh, that valley over there is extremely low. I think that's where the lowest point would be. You'd then have to get in the valley, look around everywhere, try to find the lowest point yourself, keep walking to find it. And with quantum computing, they basically use a superposition to check every location at the same time and then just hone in on exactly where that lowest point is. But instead of each spot that they have to check themselves, they're checking every spot at the exact same time. So I know that the definitions I was giving weren't exactly perfect, but it was a really awesome talk to hear about, and I'm really excited to learn more about quantum tech and computing and what's coming in the future for it. Thank you.